I'm David Castle, Vice President of Research here at the University of Victoria. And I wish to begin tonight's event by acknowledging with respect the history, customs, and culture of the Coast Salish and Straits Salish peoples on whose traditional lands we meet today. It's wonderful to be here with you this evening as we participate not just this exciting Changemakers event, but what's also the first day of IdeaFest, UVic's 4th annual, and my first annual, having recently arrived in July of last year. In fact, today is, I think, my 8th month anniversary of having been here at UVic, so there you go. And this is the commencement, of course, of a week-long celebration of knowledge and creativity from across this very fine campus. I want to thank everyone here for joining us tonight, including our visitors from the Greater Victoria community, our presenters, and our on-campus community staff, students, and faculty. I know that having such diverse audience will make tonight's conversation that much richer. This evening's event will highlight the work of some of our preeminent scholars at the University of Victoria, each of whom holds a Canada Research Chair in their field. The Canada Research Chairs were instituted by the federal government in 2000 with the goal of making Canada one of the world's top countries in research and development. And indeed, the program was set out to reverse at the time what was perceived as a brain drain to other countries, but also as a retention tool to make sure that the very fine academics in this country were able to stay within the confines of our boundaries to do their terrific work. This program has since become a magnet for attracting and retaining some of the world's finest and most accomplished, many of whom at this university are indeed some of the most promising minds of their generation working at universities in Canada. The Canada Research Chair Program has indeed become a success, with the chairs also driving social and technological innovations that are having an impact around the world. We are fortunate to have 38 of these esteemed scholars working at UVic, and tonight you will hear from 4 of them. As you will see shortly, the scholars who are awarded these prestigious positions are working to improve our depth of knowledge and quality of life across a wide variety of fields. Not only are these scholars carrying out impactful and innovative research, they're helping to train and support the next generation of highly skilled people through various mechanisms, including graduate student supervision and training, teaching undergraduate courses, and the coordination of other researchers' work. In this way, the ripple effect of their research is felt here in our community, across the country, and around the world. Tonight's presenters, Drs. John Burrows, Reuven Gordon, Roberta Hamme, and Kim Venn, will each speak to their unique research interests, spanning such critical areas as marine and deep space discovery, cancer research, and new perspectives in Indigenous law. In each instance, you will see how these scholars are pushing the frontiers of knowledge in their fields, in some cases working on technologies and ideas that were inconceivable and indeed impossible until just a few years ago. I think you will also learn how the success of this research, while based in a tradition of systematic inquiry, hinges on each of these changemakers' passion, curiosity, and creativity. It is a pleasure to share this evening with everyone here. I look forward to hearing each story of discovery that is about to be presented, and to help lead a discussion with all of you following these short talks. I've also been asked to announce that today's event will be webcast and recorded for future viewing. I hope somebody will edit that incredibly botched sentence that I just read, if that is indeed the case. If you have any concerns, please do let Tara, who is sitting at the front row here, know. That's Tara. So I'm delighted, therefore, to move along with our program for this evening and introduce our first speaker, Dr. Reuven Gordon. Reuven joined the University of Victoria in 2002, where he is now a professor in the Department of Electrical and Computing Engineering and a Canada Research Chair in Nanoplasmonics. It's easy for me to say that word. I don't know what it means. And I'm going to let Reuven explain that to you in his remarks that he's going to make shortly. He is an award-winning scholar that uses laser technologies to see and even hear. You might have been seeing some of the news media reports about the fantastic work that he does. Here, objects on a nanoscale, especially shining a light on a world that was previously considered invisible. Reuven's research has many applications, from the development of sensors for the early detection of cancers to the manipulation of viruses that allow for in-depth study. So, Reuven, it'd be my pleasure to invite you up to the podium tonight. Thank you. You have the control?
I do. I'll use this one.
Okay.
Okay, thank you, everyone. Can you hear me fine? That's good. Okay, so I'm talking about technologies for cancer research. And specifically, I'm going to be talking about detection of cancers, early detection of cancers, and, as well as studying cancer and looking for cures. And all of these technologies are related to light. So like the light coming out of this laser pointer over here. So cancer affects everyone. 1 in 4 people will die from cancer in Canada. And of all the different cancers that we have, the ones that are hidden are the most deadly, like lung cancer, because it's not until the later stage that we actually detect that someone actually has that cancer. Just to give an example, the 5-year survival rate for lung cancer, if it's caught in an early stage where it's localized, is about 50%. But if it spreads significantly, then only 1 in 25 will survive. So this is a serious problem, obviously. We're looking at a promising technology for early detection. Okay, this is working with a company in Vancouver, and they use a clinically approved drug for other uses, but they're using this for early detection of cancer. And the way that this works, this drug is called amantadine. The way that this works is the body, if you eat this drug, the body will process it very actively if you have a cancer, a tumor. Okay? So this processing of amantadine is heavily upregulated in tumors. And so as a result, in a urine sample, you'll see a lot of this processed form called acetylamantadine. So the way that the technology works is we want to detect how much of this acetylamantadine you have in your urine, and that's the simple test, to see if you're high risk for an early stage cancer. So that whole process is in third stage clinical trials right now. What we're working on is the detection end of that technology. So we want to detect the acetylamantadine in urine, and we wanted to do it in a way that's low cost, very sensitive, so that everyone can use it and it's effective, but is also fast, so that you can screen a lot of people quickly. And so the approach that we use is called Raman spectroscopy. But without going into the details, essentially we're looking at either, this is what the drug looks like before. It gives you the spectrum with all these peaks, and this is what the drug looks like after you've added this acetyl group, okay? So you can tell the difference between these two, and that's the signature that we use to tell if somebody is high risk for early stage cancer, okay? And this is the setup that we've built to do this. It's very low cost. The problem with using this process that's called Raman spectroscopy is that it's very weak. The chances of winning the 649 are 1 in a million. The chances of a Raman photon or a photon Raman scattering is 1 in a billion, okay? So it's a very weak and inefficient process. So the question you might ask is, why would you use such a weak process to try and detect a very small amount of a drug in your urine? Nanograms per milliliter amounts. And we've actually been able to use nano antennas and cages to actually do this, okay? So we've managed to reach the nanogram per milliliter sensitivity levels by combining nano antennas, which are basically antennas that you would expect to see in your cell phone or antennas that you see on the roofs of buildings. But these are antennas that are for light. And the way that these antennas work is they take the light and they focus it down to the size of the molecules that you're trying to detect. So by focusing it down to really small scales, we're able to actually look at the molecules at these very low concentrations. In addition, we use these special linker molecules that capture specifically the acetylmantidine from solution. And so as a result, we not only concentrate the light at the surface, but we also concentrate the molecule that we're trying to detect at the surface. And putting this all together, we're able to achieve the relevant levels that we need for clinical detection. Okay, so that's an example of a technology where we're trying to detect earlier stage cancers. Okay, so I'm going to switch gears a little bit, and I want to talk about proteins. Proteins are amazing machines that do everything in your body, and I'm going to get back to cancer research, but I just wanted to show this video quickly. Just to drive home the point that proteins are really amazing machines that can do all the work inside your body. Okay, so this is showing the replication of DNA. It's actually, the video is slowed down for some reason here. But it's taken from a presentation given in a TED lecture. But what it shows you is that DNA can be broken into two parts, and then this protein complex basically assembles copies of the DNA on either side. And this is happening in all your bodies right now, and it's just showing, it looks like an assembly line. It looks like a machine, right? And this is exactly the way that I see proteins as machines, okay? So trying to understand how they work and what happens when they don't work is part of my research, okay? So in particular, we're interested in this protein. It's a usual suspect in cancers. It's called P53. P53 is also called a tumor suppressor protein or anti-tumor protein. Okay, so in about 75% of known cancers, it's been said that this protein is mutated in your body. And what it does in your body is it somehow tells the body when you have a mutation that could lead to cancers, and it's the body's natural protection mechanism against cancers. So to understand how this protein interacts with DNA is a very important problem, okay? And that's what we're trying to study. So how do you study the interaction between this protein and DNA? So now I'm going to go back to nano antennas again and light. So we use a laser tweezer setup. So essentially, it's a microscope where a laser gets fired in from the bottom, and then we have this chip over here that has a nano antenna on it. And this nano antenna is a double nano hole. It's basically two holes drilled into a metal film. And we shine a laser light through this nano antenna. And what you have here is particles floating around in solution, and there's a laser beam shining through this double nanohole. So this is the intensity of the laser beam through the double nanohole, and these are particles that we want to detect. When all of a sudden a particle gets trapped in this nanohole, we see a huge jump. This is actual signal. This is actual data that we take. We see a huge jump in the transmission, and that tells us that we have a little nanoparticle there. Okay? And so this nanoparticle, then we can study it just by looking at the light transmission. It's as simple as that. I should dumb it down. Okay, that's the technology, but I'll just show you what we can study. Okay, so there's lots of things that are in the nanoscale. You've probably heard of like nanotechnologies like transistors and computers. And then there's things like molecules and atoms that are really tiny. We're somewhere in between these two, okay? So we're looking at things like DNA and protein complexes and viruses. These are antibodies. And you can also look at other types of materials that are all nanoscale, okay? So what we do is we use our laser tweezer, nano tweezer, to hold on to a hairpin of DNA. This is a DNA a little fragment that's being folded on itself, okay? And when we trap this hairpin, we see a jump in the laser transmission intensity, but we see another jump because what the laser tweezer actually does is it pulls apart the DNA, okay? So we see two steps. But if you add in this P53, this anti-tumor protein, what it does is it binds the DNA and it makes this middle step longer. So this shows the time of the middle step. And as you see, it's much longer for this red curve when you add the P53 than it is for the blue curve when you just have the DNA there by itself. So what happens if you have a mutated form of the P53, the type that would lead to your body not being able to suppress a cancer? Well, you can't tell the difference between the red and the blue curves. basically, what this is telling us is that the P53 can't stop the DNA from unzipping. It allows it to continue in the process of replicating itself and creating proteins and all this stuff. Okay, so that P53, that mutated form, is broken. It's not doing its job. So how would you use this in drug discovery? The way that you could use this in drug discovery is if you came up with some sort of small molecule that could correct the effect of this mutation in P53, then you could run this exact same experiment and see if this time step gets longer. So you take the mutant type of P53 and see if all the drug candidates that you're testing make this time step longer, so basically it starts to act like the real wild type of the P53. Okay? So that's how this can be used as a drug discovery technology to help suppress cancers. Okay, so finally I want to talk about listening to proteins, and using the same technology, the same optical nanotweezer, we can listen to the sounds of proteins. And proteins, they move around all the time. And these motions look like this is conal Boomen. And you can see that it's basically dancing in a whole bunch of different ways. Okay. But what we can do is we can, when the protein is in our laser tweezer, we can watch its motion, and we can actually stimulate it to vibrate at very high frequencies in the gigahertz range, which is higher frequencies than your computers operate at. And so we can actually listen to the sounds that these proteins make. Okay? So this is, we've scaled down the sounds to audible frequencies here. So this is what a protein like conal Boomen would sound like. And a smaller protein like carbonic anhydrase will have a higher pitch sound. So that's what that would sound like. Okay, and then we can also listen to proteins and what happens when you bind things to them, like streptavidin and biotinylated streptavidin. Okay, there's a subtle difference there. I'm not sure if you heard it. But essentially you can, I can play it again. There's a difference. But, let's see here. Okay, it's very subtle. But you can tell that this small molecule is binding to the streptavidin, and so we can see this in the acoustic signature of this protein. Okay. And another thing that you can listen to is viruses, it turns out. So we've started listening to bacteriophages. These are not harmful viruses for humans. They are harmful viruses for bacteria, though. And this is what this sounds like. It's bigger now. And so it has a sort of a lower pitch sound. And it's kind of interesting because it almost sounds like a chord. It's got almost very harmonic structure, this virus. Because what the virus is there's a protein shell around essentially water. It's a capsid of protein around water. And so it's almost like a drum membrane, a spherical drum. And so you might ask yourself, what is this useful for? Well, one is you can tell which viruses you're looking at, what stage the virus is at. And you can also think about things like if we manage to hit this virus with the exactly specific frequency that it resonates at, we might be able to blow it up and essentially disinfect against this virus. So a lot of people have actually been thinking about that for many years. And so now we've shown ways where we can get these really nice curves that show the virus's spectrum. Okay, so just to recap here. What we're doing is we're using light, and we're using it to look at biotechnologies, and specifically as the story relates to cancer, we're hoping to be able to detect cancer at earlier stages in a way that can really be used by everyone. So in a way that is low cost, in a way that is low cost and fast, and easy to use and reliable. We've been looking at proteins and exploring the interactions with DNA and with other molecules, particularly for applications in drug discovery, also looking at cancer drug discovery. And we're listening to proteins and how they interact to learn more about them, to learn how they work as machines. And we can also listen to other nanoparticles like viruses, and this could also be used in diagnosis and treatment of those viruses. Thank you. Cheers.
Tara, are we doing a test tonight? Yes. Can we hold questions until after we...
Can you turn down the lights a bit so that we can...
That we can do, I believe. Do we have the panel live? Lighting, lecture. Ooh.
Too dark?
Good? Yeah? Oh, good. All right. Okay, so no test? No test tonight. It is? Okay. Thanks very much, Reuven. That was incredibly interesting. I think you're going to get lots of questions about that. So now I'd like to introduce our next presenter, Dr. Roberta Hamme, who is an associate professor in UVic's School of Earth and Ocean Sciences and holds a Canada Research Chair in Ocean Carbon Dynamics. She is a leader in her field of ocean carbon dynamics, an area that has become critically important for us to understand as we experience a progressively warming climate. Her research is helping uncover the secrets of how carbon moves through our oceans, how this is changing, and how we can use this knowledge to better predict climate change. So, over to you, Roberta. Thank you.
Oh, I was hoping this was going to work.
Was it the other one?
Okay, we'll just use this.
You have to give Reuven's presentation again.
I'll just give you my laser pointer.
Okay. I'm sorry, I got in there.
Thank you. Okay. Carbon is arguably the most important element to us. It forms the basis of life on our planet. It also forms the basis of our energy economy, and the result of that is increasing carbon dioxide in the atmosphere. Because carbon dioxide is such a powerful greenhouse gas, this is having big implications for climate on our planet, and that has important implications for future generations. And to me, that's also a personal issue. This is my contribution to future generations right here. So I want to tell you today about my own research, but also kind of what the big questions in my field are. I'm a chemical oceanographer, and I'd say the kind of the iconic image in our field is this one. This is atmospheric carbon dioxide measured at Mauna Loa Observatory in Hawaii. Started in 1958, and this is pretty close to the present here. This is units of ppm, so what that means is that right about now, of every million molecules of air in molecules in the atmosphere, 400 of them are carbon dioxide. Now, it's a little bit ironic, maybe, that an atmospheric record is the iconic image of an oceanographer. So I want to kind of explain why that is a bit. The red line is if I try to, starting in 1958, figure out how much the carbon dioxide in the atmosphere should be if all the fossil fuel carbon stayed in the atmosphere, it would look like that red line. So only about 57% of what we're burning and putting into the atmosphere actually stays up there. And I think you can guess where the rest of it is going, or I wouldn't be up here. It's going mainly into the ocean. So that's a big part of what we're looking at. So I'm going to talk about why the ocean is such a big player. This is my not very artistic representation of the carbon cycle, but I hope it's going to get the point across. The black box is supposed to represent the atmosphere. So if I could go out and I could strip all the carbon dioxide out of the atmosphere and take the carbon out of it and weigh it up, I'd find that we had about 844 gigatons of carbon. Each gigaton is a million metric tons. That's a lot of carbon. If I went into the green box, that's my terrestrial biosphere. So if I added up all the land plants, but also all the organic matter in the soils, I get a bigger number, 2,500 gigatons. But now if I go to the ocean, 39,000 gigatons of carbon. Much, much more in the ocean than we see in either the terrestrial biosphere or in the atmosphere. And that makes the ocean kind of the big player in the room. It's like maybe the atmosphere is sort of like the serfs, and terrestrial biosphere, maybe some feudal lords, and the ocean is the king here. They has the control. Now, that's really different for a gas, that so much of it should be in the ocean. If we think about a gas like oxygen, if we look at the atmosphere in the ocean, over 95% of it is up in the atmosphere, and just a little bit, less than 5%, is down in the ocean. And here we have the opposite effect for carbon. And that's because carbon can exist in different forms in water. So when carbon dioxide meets water, and there's lots of that in the ocean, it combines and we form carbonic acid. Here, you can rip one of the hydrogen atoms off carbonic acid and you get a bicarbonate ion. You could rip another hydrogen off. You get this carbonate ion. The names aren't really important. I just want you to get that there's 4 different forms that carbon dioxide could exist in the ocean, whereas most gases, you just have 1. So that's why the ocean can hold so much. Now, one of the main things then that my field tries to do is to understand how much of this carbon that's not in the atmosphere anymore is getting into the ocean. And this is kind of a summary plot of that. So this is a cross-section through the Pacific. If we could kind of cut the Pacific Ocean in half and look at it, the Southern Ocean is down here. We're kind of up here in the north. And this is depth. So the surface is at the top going down. This black part here is the land, the seafloor. And this is showing the anthropogenic carbon. So people have gone out and they've collected water at all these different depths and all these different locations, measured the amount of carbon, and figured out what part of that is anthropogenic or there because of us due to fossil fuel burning. And this is the distribution. The warm colors here, the kind of reddish colors, are high. You can see those high colors are all at the surface. That makes sense, right? It's in contact with the atmosphere, and that's where it's coming from. So it's absorbing out of the atmosphere, and it's ending up here in the surface. In the Pacific, we see almost none in the deep ocean at all, and that's because this deep ocean is very old. The ocean turns over very slowly, and so that water has not seen the surface since before the industrial age, so it can't absorb this extra carbon yet. So that's sort of one big part of what we're doing, is that allows us to say, how much of the difference between this curve of the actual observations here and what I sort of predict it should be is gone into the ocean. Now, the other big thing, and the thing that I think about a little bit more, is, well, what's that difference going to do in the future? How do we figure out how that's going to change? And to do that, we have to look at what's happening naturally in the ocean as well. Okay, so this is a kind of a similar figure. Again, we're in the Pacific. We've got a cross-section here, but now instead of looking at just the anthropogenic carbon, we're looking at all the carbon. I'm going to add up all those 4 forms that I talked about. And this is the total amount. There's some really cool distributions here and patterns. What I want to really focus on for this talk, though, is to notice that the blue colors right at the surface are lower, and the red colors down here in the deep are higher. So the ocean has natural mechanisms that take carbon out of the surface ocean where it would be in contact with the atmosphere, and it stores it down in the deep. And these mechanisms are a biological one and also a physical one. So I'm going to talk about what those are, but we really need to actually understand them independently in order to predict them. The tools that my field uses to predict future climate and future carbon are these big climate models. So these are numerical computer models. People split up the atmosphere and the ocean into lots of little boxes. All those boxes are talking to each other. There's processes, biological and physical processes happening within each box. That's not what I do. But what my work does is inform that so that we can get what's happening in those models right. Okay, so we've got this biological mechanism here, and we've got a physical mechanism. I want to talk about each of them now. The biological one just has to do with where photosynthesis happens in the ocean. It's happening all right at the surface because sunlight only penetrates maybe a maximum of 100 meters into the ocean. That's not very far. So right at the surface, we have plants, mostly microscopic plankton. They're taking up carbon dioxide. And when they die or they get eaten by something else and that dies, those things are heavier than water and they sink into the deep ocean. And down here in the deep ocean, they are degraded by bacteria and they go respired back to carbon dioxide. So we have what we call a biological pump. CO2, carbon dioxide gets taken up in the surface. Those organisms die and they sink down here, and the carbon dioxide is released down here. So it's a way of transporting carbon down into the deep. My lab is trying to quantify this process, and we do it by looking at the amount of oxygen here that's produced. I want to talk a little bit about how I do it, because Okay, so we collect these flasks of water. This is what they look like. They're actually about that tall. Out at sea, so my students or I go out to collect those. This is a little picture of my lab. So this is a little custom vacuum line that I designed. It could look a little bit cooler because a lot of it's glass. You can just see through the glass. It looks better in person. But it takes out all the stuff that would interfere with the measurement. Water vapor, stuff like that. And then I take the sample over here. This is my mass spectrometer. It's kind of like my third child a little bit. And there I measure the amount of oxygen in the sample. This process for each sample takes about an hour for this measurement. The measurement I'm going to talk about in a few slides takes actually 2 hours. So we're not focused on getting a lot of data. We're focused on getting a smaller amount of really, really high quality data. Okay, so that's kind of the biological mechanism and how we're going about trying to understand that part of it. The physical part has to do with the way the ocean circulates. So the deep ocean is mostly really cold, about 2 degrees Celsius. And most of the surface of the ocean is quite a bit warmer than that. Now, cold water can hold more gas in it. That's actually the opposite of salt. Like if you want to get more salt into water, you could put a pot on your stove, you could heat it up, and you could get more salt to dissolve. Gas is the other way. It's the cold water that can really hold a lot of gas. So as this water moves down from the surface and fills the deep ocean, it's carrying this large amount of gas with it. And that process, water moving from the surface down into the deep ocean, only happens in a couple places, one in the Southern Ocean and the other one in the North Atlantic. So here's a nice little diagram of that. We've got the Gulf Stream coming up here. It's warm and salty, comes up into the very north part of the Atlantic. And then in the winter, we've got cold air blowing off of Canada, a lot right now, right? And coming off of Greenland, it cools down the water, so it gets really cold, it's really salty, and that makes it heavy, dense. It sinks into the deep ocean, and with it, it carries the gases that are dissolved in it down into the deep. So I really want to understand how this process, what's happening there, is affecting the gases. And I do that, again, actually not by measuring carbon, but by looking at some rare gases. So I measure neon, argon, krypton, and xenon. These are all noble gases, way over here on the right side of the periodic table. They're totally inert. They don't interact with anything. They don't participate in reactions. And that's great for what I want to do, because I want to get at the physics of this. So they don't have anything, they have no biological signal at all. They just tell me about the physics. I also measure nitrogen, which in most cases could be, N2 is pretty biologically inert as well. So this is just an example that I want to use to kind of talk a little bit about how we do it. This is measurements of these 5 gases that happens to be at Hawaii, or off the coast of Hawaii. And I'm showing here the difference between what we measure and what we expect at these different depths for the temperature and salinity. That's not important. What I want you to really look at here is in this deep water, that the gases are different from each other, right? They kind of separate out down there. Neon is the black one, it's kind of higher. Then nitrogen, argon, krypton, xenon is the lowest one here. And that has to do with their different physical properties. Some of these gases are a little bit more soluble than the other ones. Some of them are a little bit more temperature sensitive. I talked about that really rapid cooling that's happening when deep water forms. And that affects some of the gases more than the other ones. And so what I can get by measuring all of these is just sort of a fingerprint of these processes that are happening when deep water forms. I get an idea about the cooling. I get an idea about how atmosphere and ocean are interacting with each other, the way bubbles affect that. All these distributions tell me about that. And then I can take that information and I can apply it to a gas like carbon dioxide or oxygen that has both biological and physical components. So I get just the physical part out of this. Okay, so we hear a lot about carbon dioxide in the atmosphere, and today I wanted to tell you about the secret life of carbon, which is that a lot of it is down in the ocean. And because it's so much of it there, it's actually ultimately going to control the atmosphere. We need to really understand the processes and how big they are that are moving carbon around the ocean in order to predict that future. And I'm doing that by making measurements of dissolved gases. Thank you.
Thanks so much, Roberta. So our third speaker this evening is Dr. John Burrows. John is a professor in the Faculty of Law here at UVic and holds a first-tier Canada Research Chair in Indigenous Law. John has been at the forefront of Indigenous legal education initiatives in Canada, having developed programs of research and teaching at a number of other Canadian universities and now, very fortunately, here at the University of Victoria. John is an internationally recognized scholar in the field of Indigenous legal traditions and Aboriginal rights. He is a social innovator who asks us to reimagine our current legal system and find ways of incorporating Indigenous people's legal traditions to both enrich and improve our own. John, the stage is all yours. Thank you. I think we're using that one. You're good.
Bonjour, Nidinwe Makanidok, Nija Nishnabeg, Nij Marzig, Bangietago Ninita Nishnabem, Gigujitu Njinishamayan, Giganos Indijnakas, Neashi, Nigabing and Donjaba, Nigigin Dodem. I'm grateful for the opportunity that I have to be able to speak to you this evening about Indigenous law in Canada. What you have here is the representation of a wampum belt. This is a treaty that was entered into between First Nations in central Canada and the Crown in 1764. There were 2,000 people gathered representing 22 different nations to be able to create a relationship of peace and friendship and respect. In many ways, this treaty is at the foundation of Canada. This is one of our most important constitutional documents because after the 7 Years' War and at the Plains of Abraham, Indigenous people still held the balance of power and were able to do what they wanted in relationship to the British. And so in order for the British to be able to expand their settlements across Canada, they needed the cooperation and the friendship of Indigenous peoples. And this treaty is a representation of how the people would live together. You see here that they have their arms linked together. You see that their hearts are very much a part of the way that they're going to be relating to one another. This idea of coming together in peace and in friendship and working together to be able to create the laws of Canada is actually an old idea, but it's one of those ideas that needs to be reinvigorated. Because what's happened throughout our history is that this agreement, which was entered into at Niagara, of course has spread as Canada has spread from beyond this Great Lakes region. And one of the things that I try to do in my research is talk about how Indigenous peoples' laws can go from these points of origin, which are recorded in treaties across hundreds of years in Canada, to make sure that we keep our eye on living together in this peaceful and respectful way which facilitates friendship. And so we have this expansion of the idea of Canada moving beyond the Great Lakes, of course, spreading across the prairies into the north and into British Columbia. But there's another way that these ideas have spread. They've also spread through the generations. Here's a picture of my great-great-grandfather. His name is Peter Giganos Jones. He lived at a time when treaties were signed regarding particular pieces of land in Ontario. In this case, you see the treaty medals that he's wearing around his neck. In 1854, he signed a treaty dealing with 1.5 million acres of land in southern Ontario, which deals with the Bruce Peninsula, which is where my reserve is located. And through his efforts and those of his partners in the Crown, there was an agreement to be able to share the land again in peace and in friendship and respect. This is a picture of my great-grandfather, Charles Giganos Jones. He lived in an era where he was given the responsibility to be able to implement the promises that were found in the treaties. He lived off of the reserve and on the reserve for most of his life. He lived to be 100 years old. He was the last hereditary chief in our community and the first elected chief under the Indian Act, and he lived with this document of the Indian Act for over 50 years. The Indian Act, unfortunately, parts from that vision of peace and friendship and respect, which is laid out in that wampum belt, because it puts one party over another party and says that the Canadian Parliament is the one that's solely responsible to be able to create the laws by which we live together in this country. And unfortunately, his good ideas, his good heart was something that was not able to be as strongly a part of the development of the relationships in the country because of that document known as the Indian Act. Then the idea continues to spread as it goes to the next generation. This is my grandfather, Josh Jones. I remember this day as we were fishing out in the lake in Georgian Bay. He told me many of the stories that were reflected in this presentation about the treaties that went back to the foundation of Canada, what his own great-grandfather did to be able to share the land with those that came, what his own father did to try to ensure that the Indian Act didn't swallow our own legal-making authority. This is now a picture of my mother and myself. And in our generations, you have, particularly in my mother's generation, the effects of residential school, the effects of poverty, the effects of great disenfranchisement, as it's difficult even now to be able to raise to the same level as other people in terms of employment, healthcare, education. All the social indicators for Aboriginal peoples are extremely low compared to the general population. And part of what she passed on to me is an attempt to be able to understand the need to return to that place where our own laws, our own criteria, our own standards of judgment were intermingling with other people to create a country which again takes us back to a place of peace and friendship and respect. This generational view of treaties is of course something that continues to spread. This is a picture of my daughter at powwow a couple of years ago in her jingle dress. She represents the future of what occurs as we need to think about how our children and our grandchildren and our great-grandchildren are going to pick up the task that's been passed to us by our ancestors. This is the resting place of my ancestors on the reserve, a very peaceful, a very quiet, a very happy place as we remember those ideas that have spread both across Canada and through the generations. One of the things that I try to do in my research is think about ways that people can understand more fully what Indigenous law is. And that is, in many sources, one of those sources of law that we have as Indigenous peoples is embodied in our creation stories, our sacred stories about how we came to live in these places. The Hulkaminam and Saanich people have creation stories about these mountains around here and floods and tying their canoes to these mountains. And from these stories come standards for judgment, criteria of decision making. There are ways of finding these stories and pulling out guiding principles to be able to apply in our lives today. This idea of law that's in the sacred, of course, is not so unfamiliar to Western law either. For the past 5 years, I've been teaching at the University of Minnesota Law School, teaching U.S. constitutional law. And it's often the case that people there look to the Founding Fathers in a way that almost mirrors a sacred text. The idea is that there's something that those founders did that is given deference because of the wisdom that's located in those agreements and in that document. And likewise, we find in the stories, in the treaties, those things that are given deference, that are given greater reverence because of the wisdom of the people at the time they were formed. But our laws extend beyond the sacred. We also have laws that are in the environment. One of the most striking things about practicing law in an Indigenous context is drawing analogies from the physical features that you see in the world around you. This feature here is about this time of year in Ontario. It's called Abawa. This is when there's a mist that rises across the land. This mist is when you get a little bit of a melting that starts to occur. Things start to flow in that melting. You get a bit of a running. You get a bit of a warming trend. This idea of looking to the environmental phenomena is then something that's taken into the physical, into the legal world, as we have this concept is also related to the idea of forgiveness. So Abawa is the water mist phenomena. Abawa Waindam is the word for forgiveness. What does forgiveness mean? It means that things start to flow, that there's a warming trend, that there's a loosening that occurs between people. But of course, forgiveness doesn't immediately bring clarity, right? You need the application of light and heat through a period of time in order for you to be able to see more clearly. Much of Indigenous law is based on this process of drawing analogies from the natural world around us. So when I help students and communities understand about Indigenous law, we talk about how to read the land. We see the legal archive as actually being the earth, and we find the text for our decisions based in the interactions of some of the things even that we've been talking about this evening, because this is not just something that's a once upon a time way of reasoning about how we behave today. Of course, we are contemporary peoples. We want to take account of science and other phenomena and influences in drawing these analogies into our behaviors. We also have laws that need to be taken into the human world. So the things that come from the creation stories and come from the treaties and come from the environment have to be deliberated upon. We have to find ways to be able to persuade one another about what is the best decision to be able to take in the present context. So some of these decisions are formed in gathering in circles and talking with one another in those formats. We have a beautiful big house here on the campus, the First Peoples House, where you have feasts and potlatch-like events, where in that forum, people deliberate with one another, persuade one another about what's required to be able to ensure that we not only create good laws for our own communities here and now, but also think about the laws that need to be a part of our broader society. Some of our laws are very much based on prescriptions. The idea is that our laws can be declaratory. They can be rules, they can be chronicles, they can be lists of do's and don'ts. Prescription is something that is much more familiar to those trained in a common law tradition. When you look at legislation, you have something that's prescriptive, something that's declaratory, something that can be taken in to your own communities in terms of guidance and rules and regulations. And First Nations can take what we find in the sacred, in the environment, in our deliberations, and we can write them down. One of the things that I've enjoyed doing at the University of Minnesota is working with tribal courts, working with tribal constitutions, working with tribal legislation, First Nations peoples writing down their own laws, and also having their laws not only govern on the reserve, but govern off of the reserves as well. So if you go south here to Washington State with the Pacific Fisheries Commission, you find that Indigenous peoples have the ability to be able to regulate their relations on and off the reserve, likewise around the Great Lakes. Even here in British Columbia, there's something called the Coastal Guardian Watchman Network, where many First Nations up and down the coast are using their laws in ways that I'm describing to be able to make decisions about how many fish to take, how to regulate interactions with the bear population, mining, forestry, minerals, etc. When people think about First Nations law, often the most dominant form that we consider is custom. These are ways of behaving that have accumulated through the generations, and there's incentives that accrue to you that if you act in an appropriate way, you get more of the goodies, you get more of the honor within the community. Of course, if you fall outside of those customs, you find yourself not being able to accrue the same kind of opportunities within the community. This idea of customary law, of course, is something that's present throughout our communities. It's also present in the common law. In fact, much of what we do in the common law, when we practice that tradition, relies upon customs, established ways of doing things through the years, which aren't necessarily always written down and don't take the form that you might think law takes when you think about statutes or think about court judgments. One of the things that I'm interested in is then taking that treaty tradition that I've talked about that has extended through Canada and is hopefully going to continue to extend through these lands in British Columbia, and also extended down through the generations, and think about how can this be introduced within an educational setting. So one of the things we've talked about at the University of Victoria, and we have approved in principle by our faculty council, is the development of an Indigenous law degree. An Indigenous law degree would be a way for peoples, Indigenous and non-Indigenous, to be able to be exposed to these different sources of law that I'm talking about. Right now, you can go to many law schools across the country and you can learn about the beautiful tradition of the common law and how it helps us in our lives be able to resolve our disputes and regulate our behavior. And if we are in Quebec, you can go to civil law schools, McGill and Sherbrooke and University of Montreal, other places, to learn about what the Roman legal tradition has to teach us as to how we interact with one another. But nowhere in Canada right now can you go and start to engage in a formal, official process of legal learning that takes us through a similar type of journey that we see with the common law and the civil law. And that's one of the things I'm excited about. To be here in Victoria is to see the innovation that happens around developing this degree as we teach it in a way that compares and contrasts the wisdom of these different traditions and find in those moments syncretic insights that again can regulate our behavior and guide our disputes. So how do we do that? Some of this obviously can occur in the classroom. I teach not only US constitutional law but also Canadian constitutional law. I envision, and I do this from time to time in my courses, in teaching about federalism, how the provincial and federal government divide their powers between one another, and also about the Canadian Charter of Rights and Freedoms. But then I could also introduce my students to Anishinaabeg or Ojibwe or Chippewa legal traditions, which are the communities that I'm from, regarding how we constitute ourselves. And so through that first year, by comparing what's going on in Canadian law and comparing what's going on in Indigenous peoples' law regarding the Constitution in the classroom, the students can start to get an understanding of what an intersocietal way of linking arms together constitutionally might look like. This, of course, could occur in other subjects, as my colleague could teach property law and put that aside Gitxsan law. Tort law could be put beside Hukaminam law from over the Malahat on the other side of the mountain there. So these things can occur in the classroom. Of course, we can also take individuals out into the community and have them practice these forms of law that I introduced earlier. And I've had the privilege of being able to take some students out individually from time to time and apprentice them, as it were. Have an articling-like experience, to have them learn the different modes and ways of engaging regulation and dispute resolution. Of course, we can then also go out in groups. And one of the plans of this law degree is to create field schools with intensive experiences of smaller cohorts, pods of students that would be able to work with elders, work with councils, work with communities. Right now, I'm working with 30 Ojibwe or Chippewa or Anishinaabe communities in Ontario dealing with constitutions. And I would be inviting my students as a part of this process. The pictures that I've been showing you here are from my own reserve, the Cape Croker Indian Reserve in Ontario, about 4 hours north of Toronto on the shores of the Bruce Peninsula. And many of the prominent images you see are of these escarpments. These escarpments have great meaning for us in reading our law. One of the things I see as I look at these escarpments is I recognize our stories in relationship to these, and I see that we have a time depth in being able to talk about our laws. I also think about the surrounding environment in relationship to these escarpments, and I see the intricacies not only with the time depth, but the reflection that's found in the beauty that's a part of our laws. Our laws are there, and they flow from the creativity of our people, both from moments when we live in harmony with one another, but our laws also flow from those moments of conflict. Law is based in both agreement and dissent. And these escarpments, being formed through great processes of conflict as well as moments of peace, help me understand what needs to be done as I take that image that was on that wampum belt that I showed on the first screen, where people can link arms together with good hearts to be able to see the way that all of our legal traditions can guide us in this place that we call Canada, that we love, that I love, that I hope we can find ways to be able to regulate our behavior, resolve our disputes in a participatory, a democratic fashion that honors all of our relations. Miigwech bizinduig meet you. Aha. Thank you.
Thanks so much, Sean. That was very inspiring. So, one more speaker to go. So I'm sure you'll all recognize Dr. Kim Venn from the wonderful photograph that appeared in the Times Colonist on Sunday. And the Times Colonist, of course, is a great sponsor of IdeaFest. And Kim is going to take us on a journey away from Earth to stars as old as the universe. Does that actually make sense? Can they be as old as the universe? You're going to tell us. Kim is a professor in the Department of Physics and Astronomy and has held the Canada Research Chair in Observational Astrophysics since 2005. Her research aims to use the chemistry of old stars as a stellar fossil record to understand galaxy formation and evolution. Her curiosity about stellar history and evolution is helping unlock some of our most basic questions about the structure of the universe and our place in it. So join me in welcoming Dr. Kim Venn.
Okay, and do I get to go? Oh, good. Okay. So is yours still on? Okay. Okay, great. Thank you. Wow. I'm not quite sure where to stand or sit at the moment. It's a little bit awkward up here. But yes, it's really a pleasure to be here to give you this talk. I'm also really impressed by the number of people who've shown up for this. I wasn't expecting so many, and it's fantastic to see how many people are curious, interested, and supportive of the university as well. So thank you all for coming out. I've been asked, or I offered to talk about unlocking the structure of the universe and our place within it. What I'm really driven by and really interested in is technological advances. And what I wanted to show you is how the technology that we're using right now to study cosmology, the earliest times in the universe, the most distant objects, the first stars, also is related to the technology we're using to search for new planets, exoplanets, planets around other stars and their atmospheres, and to look for Earth Mach 2. So I want to start by pointing out the typical picture of the night sky that I hope you're all familiar with. I hope that living in British Columbia, you've taken the advantage to go camping and look at the night sky. And as you know, once the moon comes up, it's kind of game over. You can only see the brightest objects. It's not quite as interesting once the moon comes up. But the reason I actually wanted to put this picture up is to remind you, and you all know this, that the angular size of the moon on the sky is about half a degree, and your finger at arm's length is about 1 degree. It's just an optical illusion that looks bigger on the horizon than up, right? So there it's about half a degree. And I wanted to show you that because the deepest place that we've looked in the universe using the Hubble Space Telescope is called the Ultra Deep Field. And it's this tiny little region here. It's also got the name the Extreme Deep Field. And that is the angular size of that extreme deep field compared to the angular size of the moon. So if you take a pen and put a dot on your finger and put it at arm's length, that field is still smaller than that dot. So it's an incredibly small field of view. And the whole square there would be roughly the size of your finger at arm's length. So it's a tiny field of view. The Hubble Space Telescope has looked at it with multiple filters all the way from the ultraviolet to the infrared over 20 nights or 20 days, 20 days worth of observing. Of course, it's in space. A day isn't, you can always point away from the sun. And so they've combined all of these images of this tiny little field taken over 20 days over a 10-year period. And when we look at that, it looks like this. pretty much every single object in there, other than about 4 or 5, are galaxies. So there's a couple of stars, and you can tell the stars because they have diffraction spikes. So there's a star, there's a star. You see, there's a nice one down there. So it's almost all galaxies, other than 4 or 5 objects, which is pretty incredible. Like, that's how many galaxies there are, you know, in a point of a pinpoint at your fingertip. It's amazing to think of this. And what we're interested in now, what astronomers are interested in, is trying to put the third dimension of this picture, right? All these galaxies are not on a screen in front of us all at the same distance. They're all at different distances. So this is really where the technology is at the moment. So what we want to do is take this picture and look at it in the third dimension. And so this is the kind of thing we're trying to do now, where if this is now, this is sort of that picture we just looked at now, each one of these rings going back is supposed to be roughly 1 billion light years, or 1 billion years of time. And so those galaxies are distributed at all different locations, different distances. And of course, since light travels at a finite speed, it takes light time to reach us. So when we're looking at something that's as far away as possible at the edge of the observable universe that formed right after time, it's taken all of time for that light to reach us now. And given more time, there will be more and more things, but this is what we're trying to do. And so surprisingly, the telescopes we have now, the Hubble Space Telescope, I showed you that picture. These are the galaxies that all go back roughly almost down to this ring here, about 13 billion years. And the thing is, though, is that the universe is 13.6 billion years old, and so there's this gap in here, at the moment called the dark ages for physical reasons, but it's a region of space that we have not yet been able to probe. And this is where the next generation of technology is important. The next space telescope, the James Webb Space Telescope, will be launched in 2018, and the 30-meter telescope that Canada, just up the street here, up at the NRC Hertzberg, had the privilege of designing the 30-meter telescope, have the privilege of being the leading instrument scientists for the 30-meter telescope, and yet we are at a critical point because for the last 5-6 years, the government have not been willing to sign Canada in to pay for our membership. So we may have to actually sell our designs and our planning if the TMT, the 30-meter telescope, is not in the budget this year. So this is this little region of space that we're all trying to work at, that astronomers around the world are trying to get at, will be theirs. So it's this little region in here. What we think is right after the Big Bang, there was the formation of all the particles and laws of physics in the universe. The universe then went through a period of inflation, and then small fluctuations in that space-time continuum were imprinted in something called the cosmic microwave background radiation. So this is this pattern right here that was detected by the Wilkinson microwave anisotropic probe and has been published, and physicists have been ripping this apart, trying to understand the exact structure in our universe. But the telescopes have not been able to reach back. This is a different sort of physics experiment that was launched on a satellite. Telescopes are only able to go back about 400 million years, and the Wilkinson, the WMAP results were 400,000 years. That's a factor of 10. It doesn't seem like much, but a lot was going on in the universe back then, and so we would really like to get into that. So I wanted to show you these two telescopes I mentioned, the James W. Webb Space Telescope, which is this one here. Looks like it really, this is really what it looks like. It's designed, it's built, it'll be launched in 2018. It's really close to being finished. And the 30-meter telescope over here. And to give you an idea of the size of the mirrors, sorry, I hope I don't laze you guys. You guys all have good eyesight, right? So here's the size of a person, and here's what the Hubble primary mirror looks like. And you can see how much bigger the JWST mirror will be and where it'll be located. And then if you, rather than drawing the outer ring, if you draw the inner ring, that's roughly the size of a large telescope, a 5-meter telescope here on Earth. But of course, the largest telescopes currently that exist on Earth are the Keck telescopes, which are in Hawaii. And these are multi-mirror telescopes. So each one of these is about 1.5 meters, and you stitch them all together and they all point to the same secondary, and that's how we focus the light. There are other large telescopes. The Subaru 8-meter telescope is also in Hawaii. The Gemini 8-meter telescopes, there's one in Hawaii, one in Chile. There's the VLT, the Very Large Telescope, which are 4 8-meter telescopes. But this is the largest, Keck, and there's 2 of them, Keck 1 and 2, right beside each other. And then you take that same design and you blow it up to a 30-meter telescope, and actually the size of each one of those individual mirror segments is about the same as Keck. So when you put it into the telescope casing, here's a person, and there's a person. This is what Canada has designed. This is what we led the design on this, and this is what the next big thing in astronomy will be. At the moment, we're trying to get the government to pay for our 18% portion. It's a favored portion because of our design work that went into it, but it's a pretty impressive piece of equipment. So the one thing about any of these segmented mirror telescopes is they have to work with adaptive optics. And once we get up to 30-meter telescopes, not only the mirrors have to work with adaptive optics, but even every single instrument has to take advantage of adaptive optics. It's just the way the larger mirrors will focus light that they have to do this. So here's an example of Keck 1 and Keck 2 in Hawaii using adaptive optics. So with adaptive optics, you need to use laser guide stars. So you actually shine a laser up into the sky, which reflects a tiny spot in the sodium layer of our atmosphere, 90 kilometers up, and sends it back. And in this case, adaptive optics tends to work better at infrared wavelengths. And in astronomy, infrared wavelengths are the best wavelengths for looking at the galactic center because they actually get out of the dust and extinction in our galaxy. So in this picture, I love this picture because both of these telescopes are using adaptive optics, using the laser guide stars to observe things in the galactic center. And adaptive optics is, all it does is it takes, if the Hubble Space Telescope or James Webb Space Telescope will never need adaptive optics. They're above the Earth's atmosphere. It's only when you're observing from the ground that you have to have adaptive optics because the Earth's atmospheric turbulence just jostles that light that's coming in, those pinpoints of light that's coming in from space. So it's like if you're in the bottom of a swimming pool trying to watch birds flying by over top. The water will just jostle space, jostle that light around. So adaptive optics corrects for that. That's what we're doing with these laser guide stars. And so I just wanted to show you one picture. So here's, for example, a system. This is, I actually think it was taken with Keck. It might have been, there's other adaptive optics systems now. Everybody wants adaptive optics. But here's an image of the sky without adaptive optics. And you can sort of see there's 2 objects there. But when you turn the adaptive optics on, in other words, you point the laser up in that direction, use that to correct the atmospheric turbulence around it, and then reconstruct your image, then you can actually see there's 2 objects here, and there's 2 objects here. And here's another way of looking at it. Here's with adaptive optics off, and here's that bright object, here's a little faint object, and 2 objects in here. So you can already see adaptive optics is going to be necessary to make these 30-meter telescopes work, but you can already see that adaptive optics is also going to be really, really good for finding really faint companions around other stars, which means it's a fabulous way to look for exoplanets. So using the exact same technology that we're able to study the most distant objects in the universe to try to recreate the first 400 million years after the Big Bang, we can also use this to try to find planets around other objects, other stars. So this picture is taken of the very famous star with a very romantic name of HR 8799. And all of these lovely planets were found through very clever adaptive optic techniques by Christian Marois. He's a staff scientist up at NRC Hertzberg as well. And I wanted to show this because the one thing about all of those planets, though, is even though there's a lot of them, it was the first exoplanetary system found. They're all gas giants. So on further investigation, they all have very high masses. They're all quite distant from their host star. And because the host star in that system is quite a bit cooler than our host star, then the distances and the masses kind of scale so that they're in positions that are very similar to the gas giants in our galaxy, just sort of scaling it for the mass and distances of their host star. So it's really great that adaptive optics can find all these little exoplanets, but these are the ones that are going to be far away from the host star. What we really want, what everybody really wants, is to find another Earth, right? Terrestrial planets. So for that, we have to use something completely different. Adaptive optics actually doesn't work in this case. Here, what we have done is launched a satellite called the Kepler Kepler satellite. Kepler satellite is looking at a 6-degree field towards Cygnus. So if you're an amateur astronomer, you know where Deneb is. It's in the constellation Cygnus, and here's Vega and Lyra, and the Kepler field is the area right between those two. And Kepler has now confirmed over 1,000 exoplanets, which is pretty amazing considering it's only been around for about 5 years. And here's the angular size of the Kepler field versus the moon. So it's quite almost the exact opposite of the Hubble extreme ultra deep field. And Kepler is looking for very small changes in light from the stars in that field due to a planet passing in front of it. So if it's a large planet, the large planet will just cover up some of that light. So there'll be a dip in the light curve, and then it'll go back to where it was. It'll be very symmetric if it's just a transit. And so Kepler has found 1,000 of these things, and these things, because they're very close in to the host stars, these are much more likely to be terrestrial planets. And so there's one case, Kepler 186, that now seems to host something like a planet that's the size of the Earth in the habitable zone, meaning the distance from its host star would have sort of the average temperature that would be hospitable to life. The one thing about this system, though, it's still not really like our solar system. It's really not Earth Mach 2. It's about the same mass, but if you look at this system, it's a much, much smaller, fainter and cooler star. There's lots and lots of exoplanets that are inside, like Mercury, so it won't host life, but inside. And then this Earth-like planet is the only one that we know of that's quite far out. So it's still not quite like Earth Mach 2. This is something that we're really after. And so what I think is exciting is that if you imagine yourself out observing, maybe, or camping, enjoying the night sky, remembering that the moon is not our friend, but remembering that the angular size of the moon is absolutely huge compared to the deepest distance we've ever looked into space, and that pinpoint of light was full of galaxies, and how many there must be then over the entire spread of the sky. And then the technology we're using right now to study those systems is the exact same technology that we're using to try to find other planets. And maybe one day, this picture will be a picture taken on another planet looking back at the Earth. So I'll stop there.
I think Kim would like to get rid of the moon. All right. So thank you, Tara. We've got the lights up. And because our speakers are consummate professionals and all got their talks delivered on time, we have lots of time for question and answer, general discussion. So put up your hand and we'll start to have a conversation with these Canada Research Chairs. Yep, at the back.
I was just unclear if it was a historic wampum, and if it is a historic wampum, where was it created and where is it today, and has it ever been used in cases, in legal cases, to affirm treaty rights?
Yes, that wampum is a historic wampum. In fact, it was 250 years old last year, and there were celebrations that took place around the Great Lakes, reciting the history in great detail about how it came to be made. And there are cases that also refer to that wampum. Chippewa of the Sarnia is one that comes to mind, that talks about how important this agreement was to the creation of our country, because what it did is it recognized that lands were reserved to Indians upon the arrival of the British, and that those lands should remain in the hands of Indians until such time as there was a transfer in a public meeting, and that the party that was responsible on the government side for entering into those treaties was not the local colonies, but the distant imperial powers representative. And so, yes, it's a part of Canadian law. It's also an historic agreement that has been recently celebrated quite a bit around the Great Lakes area.
Okay, thank you. Yes.
I've got the bad one here. It's
Yeah.
It's 300 million. So the cost for Canada to have an 18% share of a $1.6 billion telescope is 300 million. So it's a if you do the math, it's a very favored cost. So 300 million will buy Canada 18% of the entire telescope. With that money, we plan to build the dome. So the cost of that will go into the dome. The cost of that will go into building the adaptive optics part at the primary mirror. So light comes down, bounces off each of those individual several hundred small mirrors that has to go up to the secondary mirror. And so the central portion that will both align those mirrors and then also fix them in real time in turbulence will cost about 80 million. And that's a contract, that is the main part of that. All those individual segments will be contracted out for. It's really that component that really defines this telescope as being something amazing. And that's what we designed up at NFC. So that's the contract that we're fighting to get. And then there's little components all over, including 30 million marketing costs and building roads. And thanks.
Yeah, thank you. Thank you to all the panel members. You're all very fascinating. My question is for John. John, we live in a multilateral governing country. We have multiple levels of self-governance and governance. In BC, as you identified, First Nations, we don't have very many treaties. We don't even have unanimity amongst First Nations around wanting treaties necessarily. And I'm wondering if you can speak post-Chilcotin, if you see the next 10 years, some of the future, what your thoughts are around multilateral governance, how First Nations may continue to strengthen their levels of self-governance, whether it's treaties or non-treaties after a Chilcotin decision.
You might want to explain a little bit about that decision, sure, so we're all on the same page.
So one of the points that I was making in the talk is that there are multiple sources of law, and within Indigenous communities, there are obviously many places that we can look as authority to be able to guide our decisions. And likewise, in the Canadian context, more generally, there are also multiple sources of law. One of those sources of law is treaties, and they're protected as the highest law of the land in Section 35(1) of our Constitution, which says the existing Aboriginal and treaty rights of the Aboriginal peoples of Canada are hereby recognized and affirmed. Well, there's another word there besides treaty rights. It's Aboriginal rights. And this last summer, the Supreme Court of Canada, in a case called Chilcotin, recognized that people in the interior of British Columbia own land that they have interacted with from time of memory, and certainly since the time that British Columbia and Canada have asserted a relationship over that land as well. What the Chilcotin case did in recognizing that Aboriginal peoples have title is it also opens up space for Aboriginal peoples to manage that land over which they now have ownership. And so what we have in effect by implication in British Columbia is a recognition that Aboriginal peoples have self-government as a part of their constitutional responsibilities. Now, the court's going to have to say more about that, because when you just rely on something that's there by implication, it's a much weaker claim than if you've got an explicit recognition. The explicit recognition is to ownership. What's there by implication is governance. But it's hard to see how you could own land without having the opportunity to say what you would do in that particular plot around the minerals and the forests and the animals and the plants and the waters. And so, yes, there are other ways that Indigenous peoples are going to be exercising their legal authorities that go beyond treaties, and the frontier of Aboriginal title law, as demonstrated by the Chilcotin case last summer, is one of those ways that those laws will be manifest.
Thanks. I thought I saw a hand down here. Yes, you.
How much of the $18 million will be actually spent in Canada on building parts of the telescope which were eventually reassembled on scientific America.
So the TMT, the 30-meter telescope, is designed to go on Mauna Kea in Hawaii. And it's partly funded by the Moore Foundation, partly funded by Caltech, and then we have international partnerships with Korea, Japan, India. And so Canada will put in $300 million of a $1.6 billion contract. Of that $300 million, we are scheduled to have the contract for the dome that'll go over top. And this dome, you saw how big the telescope is. We actually have to contract with people that build stadium domes to do something like this. And that'll be $125 million. So the contract would go to Benjamin Systems, which is a company in British Columbia. It's in Burnaby. And but then of course it will be built in Hawaii. They have to be in Hawaii. And then the Nefarious, which is the adaptive optics hub that I was talking about, that will be built up at the University of Pittsburgh, is $80 million. And that will be built entirely here in-house and then shipped down to Hawaii. And then there's additional also, there's a few other instruments. There's something called IRMOS, which is the infrared multi-optic spectrograph that would also be built here. There's also adaptive optics, like there's components of the adaptive optics that go over laser guide stars. And something that's being experimented with only in the last 2 years at the Gemini telescope, including the instrument that Ken's been involved in, is rather than using a single laser guide star, which is what I showed you, to actually make a laser constellation. And so you send one laser through a prism, and a prism sends out then 4 or 5 equal beams, and you can then correct the entire region, which is pretty exciting. So those components are on more in the order of about $25 million. So the total amount of instrumentation would be on the order of $107 million, and then the dome would be on the order of $125 million. So then there's sort of a swap. Actually, I think the total is $68 million. Comes in construction fees, operating costs, and things not associated just directly with the building.
So as you can see, scientists do budgets, especially big science projects like Kim's. Question over there.
Dr. Venn, I will be carbon-based dust long before you are. You have a view of things that I don't have. Now, 237 years ago, the Hawaiians thought they were alone in the world, and then Captain Cook appeared, and they found out they weren't. Now, do you think that we are alone in the universe? And do you have any ideas on the cause of the Big Bang?
That's where you get into metaphysics. I mean, there's even theories that sort of in the first 35 seconds or so that there never was a Big Bang. Right? But if we're talking about the first 10 to the minus 35 seconds, what happens there is unknowable to physicists as we know it. So we have to stop at 10 to the minus 35 seconds and say, so what caused? I have no idea.
Mathematics is almost back there. Mathematics is much further back than the telescope.
Yeah, that is, and that's absolutely, we're into pure theory past the moment of the colorful map, the cosmic microwave background radiation. We really can't see anything back there beyond that distance. That was at 380,000 years. So beyond that comes entirely from theory, from particle physics, looking for the Higgs boson, and things like that. The other question you asked is, are we alone? And I think that everybody in the room would have a different opinion, or the same opinion, but maybe for different reasons. And actually, I had the great pleasure of substitute teaching for one of my colleagues last year, and I had the chance to teach the Life on Other Worlds class for John Willis, who was on sabbatical. And something that came out that year in the news was that there's chemical composition on the surface of Mars that is necessary to make DNA in our oceans, and that maybe it actually takes 2 planets and early bombardment, shipping dust off the surface of Mars and having it land on the Earth into an ocean like the Earth's, in order to develop life. And so this just starts to make me think that it's not just, I mean, maybe it takes more than one planet, maybe it takes two planets, maybe it takes a certain amount of time in composition, it takes a certain amount of time for the universe to reach the chemistry with which you can then, composition with which you can then maybe build life. So is there life out there? It could be even more complicated, but even if it's even more complicated, given all of those galaxies, and all those stars, and all of those exoplanets we're finding, there must be other examples of life.
You have answered my question. Thank you.
Question over there.
I have a question for the oceanographer. Sorry, I don't talk to you on the
Roberta.
Okay. I was interested in the big daddy role of the ocean in capturing carbon, but my understanding is that there's a limit to that. As the oceans warm, perhaps the sort of unused deep water well, popping up, we may not be able to get to that, or can we, is there a limit to this repairing the thing like that?
There's two kind of limits. There's a time scale to it all. The ocean takes about 1,000 years to turn over. And so you got to wait for all that water to exceed the surface in order to suck carbon dioxide out of the atmosphere. There's some suggestions that the process in which I talked about, where surface water can move into the deep water, could be changed in some way, shut off maybe even by warming of the surface waters, but we haven't seen indications in the data of that yet. So that's still kind of a speculation. It might happen, it might not. We haven't seen it yet, but we don't know. The other thing that is slowing down the ocean's ability to take up carbon is, you may have heard of acidification. So the more acidic the ocean gets, the more those different forms of carbon that I talked about are all sort of on the acidic end of it. And that means that there's less room in the other forms for to take up more carbon dioxide. So as that process continues, it slows down the ocean's abilities, but still doesn't turn them off.
Question very far back there.
Sorry, I actually just answered the one I was going to ask about the carbon sinking in the ocean. One is for the physics. That Kepler numbers, is it true that that's only the first of a sequence of data dumps, that they've only been able to process so much, that 1,000 only represents a fraction of what they've actually been able to see, and that they've only been able to sort of figure things out, and that was just the media release, so they could at least release something?
It's ongoing. And so what Kepler does is it comes so the Kepler mission, they find candidates start to see many dips in their light. And it's only a candidate planet unless it's followed up and they can repeat the dips in light, or they can actually image the other planets. They can image them. So it requires follow-up observations. Kepler itself, just by itself, doesn't discover planets. It requires follow-ups. And so the follow-up observations are usually done with ground-based 4 to 10 meter telescopes, not just a Kepler. And so those 1,019 are the ones that have been followed up and have been confirmed as exoplanets with orbital sizes and masses and things like that.
So there could be
there's
an incredible number of potentials that just haven't been followed up.
Exactly. There's tens of thousands more stars, and there's a lot of competition now for the telescope resources, because lots of people would still like to use a telescope for their projects, but with so many candidates to follow up, you could take all the 4 to 8 meter telescopes and just have them following up the candidates, and you'd still have plenty of objects left to follow up. So there's so many candidates, and it's just that tiny 6 degree by 6 degree field. So again, the sky, and there's just so many. The Kepler field doesn't go very deep either. It only looks within our galaxy and only a little bit into our spiral arm. So it just doesn't go very deep. There's so much more potential even just in our galaxy for the Kepler field.
And I actually had another question for the gentleman doing the nanolight. When you were talking about stimulating the audible reaction, you didn't really say what it was you used to sort of create those sort of resonances, and what is it that you're actually, how is it that you're creating that sort of audible sound?
Okay, so the resonances are at very high frequency, so we can't actually hear it. So it's at hundreds of gigahertz. And
Are you stimulating it, or is it something that you're just picking up on, or is it constantly going, or are you stimulating and creating and then recording it?
We use two laser beams, and their frequency difference is 100 gigahertz. So they're pulsing, just like if you play two guitar strings and they have a slightly different frequency, you'll hear beat notes. The laser beams do that as well. And that pulsing is at 100 gigahertz or so. And we scan that pulsing, so we scan one of the laser beams. And in doing so, when you hit the vibrational resonance of the protein or virus that you're looking at, it gets pulled on by the laser beams. And if you pull on it at the resonant frequency, you'll start to heat it up and it'll start to move around. And that's how we take the spectrum. It's kind of a different way of taking the spectrum. It's a weird part of the spectrum. That 100 gigahertz range is where electronics is not fast enough, but other types of ways of measuring things like infrared type of spectroscopy, that's too high frequency. So it's kind of in this dark zone of the electromagnetics.
The molecule that you're trying to, with those frequencies, with that sort of resonance?
Yeah, well, we observe it, and so far we don't see anything that implies that we're damaging it, but we are, I personally am concerned about this, specifically if you're talking about using 60 gigahertz cellular phone bands, for example, or things like that, where you can specifically and very, very specifically heat up very specific biomolecules. So that is something to be investigated, yeah.
And is it, by the way, just while we're on this topic, is it resolving enough that you're just learning things about the mass of the proteins, or do you actually learn things about the structure of them by doing this?
You learn about structure, shape, and elastic properties. Yeah, so we learn that we can distinguish between wild-type, mutant-type proteins. Viruses at different stages the capsid will grow. HIV has different amounts of lipids in the capsid, for example. So I'm not an expert on the bio side of things, but my understanding is that all these mechanical properties we can look at.
Great. So there's a question.
Yeah, it's on the same line.
Okay, great.
I was just curious, or I wanted some clarification on your statement that this research can aid in diagnosing or identifying nuclear viruses. So am I in understanding that by being able to measure and determine the frequencies, you can then figure out whether someone's suffering from something, what exactly it is they're fighting, or what did you mean by that?
Yeah, that's kind of where we're going with this. So for example, we've been looking at a bacteriophage, MS2, which from our spectrum, that spectrum I showed, we can tell that it has a 4.5 nanometer shell and it's 27.5 nanometers in diameter. And so we can tell the characteristics of that particular virus. So if we saw those signature, if we saw that pattern, we could be able to infer its shape and its structural properties. In the same way that you could infer things about other types of viruses like HIV, which actually at different stages in its cycle changes a lot in shape and size, and so and its activity will depend on that. So it will actually tell you a lot more about that. There are other researchers working on similar things, but usually they use fluorescent markers or some other type of way of getting at the information. Here we're just looking at the sound that the object makes.
Thanks, Reuven.
Yeah, I want to thank all the panelists. It's a really good discussion. I'm going to ask Professor Borles a question. Two-part. You talked about the possibility of an Indigenous Law degree here at the University of Victoria. I wonder if you could comment on where you see that going. And then secondly, do you foresee a time, based on the kind of growing respect that the common law and the courts would have for Indigenous legal traditions, where, say, the Supreme Court of Canada would as it currently looks at the civil law from Quebec and the common law from English Canada, would also be enriched by Indigenous law traditions that they take into account as well? Is that where you see this maybe going?
Yes. So with regard to the first question, where do we see this going? I just want to take us back a little bit. Back in 2003 to 7, I think it was, we ran a program in Iqaluit teaching Inuit students the common law, but we also had Inuit law as a part of their curriculum. So I was teaching contract law, for instance, in that setting, and I'd be talking about the law of obligation that we have in Canada in relationship to contract, and some of that law that was coming out of the north. These students were Inuktitut speakers, and so they would every once in a while take what I was teaching them, and they would talk amongst themselves in Inuktitut to try to understand what obligation meant from their own linguistic and cultural perspective, and then we would have this iterative process where it was clear that what they wanted to do with contract law would have innovation in relationship to what I was teaching. And then I would leave the classroom, and for the next hour and a half, they would have an elder that would come in and would teach them about Inuit law of obligation from another perspective altogether, so that when it came time to be able to test their knowledge about how contracts can be formed or obligations that are voluntary can be formed in that site, it was very much an integrative process drawing on both of the traditions. That's where I see the program going as we move from community to community, that the Shwepnik people of the interior or the Dene people of the Mackenzie Delta will have ideas about obligation, both voluntary and involuntary, that are somewhat different from our contract and our tort obligations, that will help them think about and then work practically on the ground in entering into relationships with others. And as that occurs, and that is folded into their own legislation, their own agreements that they make with corporations, the Supreme Court or other courts will be called upon to interpret what it means when you have some Dene concept that's interacting with a common law concept. And I believe that the Supreme Court's own interpretive framework is somewhat welcoming that. They say that the law dealing with Aboriginal peoples is sui generis, which is a Latin word meaning unique or of its own kind, and that when you answer questions involving this legal universe that I'm suggesting, you, yes, look to the common law by way of analogy, but it's not determinative. Likewise, you would look, say, to Dene law by way of analogy, it's not determinative. The court has said that a morally and legally defensible conception of Aboriginal rights will incorporate both legal perspectives. And so it's in the interstice of the way that these authorities flow into one another that I think you will have the court doing what you suggest, which is actually seeing Indigenous people's law being a part of the law of Canada, being part of our common law, if you will, that helps us again regulate our behavior and resolve our disputes.
Other questions? Yeah.
Yep. I hope this is fairly simple for each of you. You're about to get your greatest wish granted. I would like to know what your wish is.
We would like to start with that one. How about Roberta, why don't we start with you? We haven't heard from you in a minute or two, so I'll put you on the spot. Your greatest wish. Okay. CO2 vacuum cleaner. The world's biggest air purifier. How about you, Ruben?
I guess just really having some sort of translational impact. I mean, a lot of the things that I'm trying to do are technologies that I'm hoping will make a difference, and to take it from the research lab out into the world where it actually makes a difference is a really big step that seldom ever happens. Everyone's trying to do that. A lot of people are trying to do that. But if I can do that, I'll be very happy. Yeah.
I think, Kim, we've got a general sense about what you're wishing for. But is there anything you'd put in as number 2?
I'd like Roberta to solve global warming. I'd like John to solve the political long-term problems. And
Well, I think one of the things that would be really important in the Canadian context is to have stronger recognition of the laboratories that are First Nations government. I mentioned work in the United States with tribal courts, and that produced a casebook that was thousands of pages long that allowed me to be able to introduce to the students the complexity of decision-making processes that Aboriginal peoples are involved in. In the Canadian setting, there are some tribal courts, but there are very few and far between. And to the extent that we had more of these laboratories, that I think would add to our stock of knowledge, both in the courts and in the academy, but of course in the communities as well, as to taking innovation around understanding what the law is in those communities.
Great, thank you. Now, for Kim, why do we want to find another Earth than Earth walk to? I just think Roberta looked at our own Earth and it's being damaged by us. So is looking for another Earth, does that help us teach about our own planet, or is it let's go with somewhere else because we're just about done here? So it's the interstellar question.
It's really fun being able to ask, even if you could travel close to the speed of light, what does it like? It would still take multiple generations of people to get to the closest star that we have at the time. Get a closest star.
Good stuff if you can hear.
I'm just another very I think that the pure curiosity to know our place and I think that's as much as times called as I love science fiction, that is pure fantasy and fun and wonderful, but it's not science. So science is just is also philosophy. So understanding ourselves.
Here, go ahead.
We've got 2 microphones here. Neither are being used, and it would be wonderful if your speaker could use microphones, please.
Any questions? Other questions? Okay, one back there. Speak loud, like, and I'm just a noisy mic person, so I'm going to keep my microphone so you can use that. All right, go ahead and speak loud.
My question is for Professor Burrows. I'm curious, I understand on the surface how your research affects the legal tradition, but I'm wondering how you see your research in aiding, replacing the Indian Act.
Yeah.
And what it means for the government of.
That's right. So if there's a recognition that there are various sources of law that can be pulled upon to make decisions, that helps to replace the Indian Act, because right now the Indian Act is 150 years old almost, and it was designed with a specific purpose to assimilate Indians so that they wouldn't be making decisions in ways that were different, in ways that were paying attention to their own desires and objectives and aspirations. The idea of the Indian Act was to make decisions that would replicate what was going on in parliamentary circles. And so my research presents an alternative to that assimilative process that has basically been unchanged since 1876. And I can remember stories from my grandfather, about his great-grandfather, when he made decisions, there was always an Indian agent at the table that would have the final word as to whether or not what the council said would be authoritative within the community. The Indian agent was removed in 1969, but right now if you pass a band council resolution, it has to go to Ottawa, and if Ottawa doesn't say anything for 40 days, it becomes law. But if Ottawa chooses to send that resolution back to you, it isn't something that can guide your community. And there's a very narrow band of allowable resolutions that can emanate from the council that will pass that Ottawa test. And for most Indigenous communities, what that means is that you are being governed by other people, that you're not able to take responsibility for your own affairs. And without being able to take responsibility for your own affairs, there's a disconnect and there's a disillusionment with the whole process of governance, with the whole process of law. This is about the very conservative notion at one level of the revitalization of rule of law within Indigenous communities, and part of that revitalization of the rule of law is getting rid of a system that is, in its oversight, dissuades people from participation. For instance, at Six Nations in Ontario, a community of about 20,000 people, there's often 300 people that will participate in the election of the chief and council, because this is regarded as a government that's purposely designed to get rid of the people. And so when you live with a system like that, what I'm suggesting is a way that is more democratically appropriate than what we find in the processes.
Any other questions? Yes.
Question for each of the panelists. We hear a lot in the media in the last few years about seismic speech and multiple. I would just be interested to know what your opinion is on that as it relates to your field of government.
I guess I'll start with that. No, I mean, as a scientist here at UVic, there's none of that for me. But I definitely see with my government colleagues in Fisheries and Ocean Canada, that they're not able to talk to the media with the same kind of freedom that I am. So I've published papers with them, and they've said to me, okay, Roberta, you've got to take the lead on interacting with the media, because I can't get permission in time. Even if something that we're going to talk about doesn't really feel like it has implications, just the process to obtain permission to speak with the media is so lengthy that the window in which everyone wants to talk to you about your paper coming out is short. They can't get it in time.
I just wanted to add one comment. As Roberta says, we at the university are fortunate, very fortunate. We're allowed to discuss our work and collaborate internationally and nationally and discuss anything. It's really a privilege. My colleagues up at the NRC Hertzberg, who have designed the TNT, cannot talk about it. They can't talk about their amazing abilities and the amazing designs. They officially are not allowed to lobby for it either. And I think that this is maybe part of the problem why people in Canada don't realize what an engineering feat this would be for us. Still good?
Yeah, she turned it on.
It's on.
Let's get the mic up a bit or something. Any other questions for our group here? Yes, very back.
Question for Roberta. There was an article in the Times Columnist newspaper last week about seagulls and how the population of seagulls, a couple of researchers from UBC who looked at seagull populations and found that they dropped by 50% since the 80s. And they also cited a couple of other species in that article. The implication was it had something to do with reduction of biodiversity in the oceans. And I'm wondering, from your perspective in your research in carbon and the ocean, whether you see possible linkages with that kind of an effect that those researchers are finding.
I'm not familiar with that study in particular. I am familiar with a number of studies where they've tried to link seabirds with the help of health of fish populations, because in areas where the fish are feeding, that's also where the seagulls are feeding, and so they see really strong linkages there. In terms of the kind of things that my research impacts in the biology, it really has a lot to do with things that have shells, because carbon is an acid. I talked about it combining with water and becoming carbonic acid, and so the more carbon that the ocean takes up, good for us, it's out of the atmosphere, but bad for things that make shells. You think about like an antacid that you put in your stomach is made up of this calcium carbonate, the same stuff that the shells of mollusks and all kinds of things, shellfish are made out of. And so from my point of view, the more that the ocean is taking up this carbon, the more that it's impacting organisms like that, and in ways that we don't really understand very well. Even whether in some cases it causes these animals to make their shells thicker, in some cases they lose their shells altogether. How does that interact once you get them out of the lab and in an environment where they're competing with other species? It's pretty unknown still.
Any final questions for them? Well, seeing none, then I would like to remind you, first of all, that there is an evaluation form available with respect to this session. You can tell us about us forgetting to use the microphones that are on the floor, so we'll read that, I'm sure. But I would like to, in closing, just thank all of you for attending this evening, for the great questions that you had and the observations that you made, and also to thank all of the presenters for their presentations, their passion, energy, their commitment to the research that they do here, and their willingness to come and spend their evening with us, discussing that research with us. So thank you very much. These are complex events to put on, and here this evening is Tara Tedesco and Sally Eshues. They're both involved in putting on IdeaFest throughout the entire week, and so I'd like to give a big round of